All right, time for the fundamental theorem of calculus, and this is a pretty important theorem at its heart. It just says that when we have integrals and when we have derivatives, that these are opposites of each other. And in fact, this is what calculus students actually think integrals are. They think, well, integrals are the opposite of derivatives. But I want you to notice that's not what we defined an integral to be. We defined an integral based on partitions and then summing up values over those partitions, either the upper or lower values within each section of the partition. There's no reason why we should think that that idea of summing all these values and finding all these areas somehow connects us with the idea of derivative and rate of change. They seem very opposite of each other. But the fundamental theorem of calculus is what makes this important connection. In fact, it's a super important moment in the history of mathematics. It's why someone like Isaac Newton or Gottfried Leibniz is considered such a genius and such an important person in math history. Okay, so the way we're going to prove the way we're going to do the fundamental theorem of calculus is first we're going to show that derivatives, if you take the derivative of an integral, you get the function out again. And then we'll show that if you take the integral of a derivative, again, you get the function out. So let's start with part one. Part one just says that if I take the derivative of the integral of a to x of f of t dt, that I get just f of x itself. And this middle part, that accumulation function in the middle, I'm going to use throughout the problem. I'm going to call it f of capital F of x. Will be that a of x of f of t dt. Okay, so what do we need to know to prove this theorem? Well, first, you need little f to be continuous. So if it's not a continuous function, then we can't go through with the theorem. And we need capital F to be not only continuous, but differentiable, so what we call a C1 function, continuously differential. So the derivative itself is continuous. Okay, so let's go about trying to prove this. And at the heart of this theorem, what we're going to have is we're going to start with A, and then we're going to go to x, and then we're going to add a little bit and get x plus h. And so we'll write out the difference quotient, and the difference quotient will end up giving us just this area right here, and we're going to try to show that that area is the same as just the height of this f of x itself. And the change in that area, right? So not the area itself, but the rate of change of that area is just whatever that height is, whenever h is quite small. And it kind of makes sense, right? Because if you imagine h being super tiny, so instead of the picture being drawn like I drew it right here, if you instead take that x plus h and stick it right next to x, then what do you notice? Well, that's pretty close to just a vertical line, and so it kind of makes sense that maybe this rate of change is similar to just whatever the height of x is times some very small change in x, so times some delta x. So that's kind of at the heart of the proof. So let's come and talk about it and see how it goes. So we're gonna do a few things. So first, we're gonna start with just a single point. So we're going to let x naught be a point in a, b. And I don't want it to be that end point over there, because then that wouldn't, it would, I don't know, it'll mess things up a little bit. But notice if it was that end point, we could kind of do the whole problem, but switch things around negatively. Okay, then let's let epsilon be greater than 0. And then what I know is because f is continuous, there exists a delta greater than 0, such that if I use the letter t because it's what we're going to use whenever we talk about these f's, such that if t minus x naught is less than delta, then f of t minus f of x naught is less than epsilon. Okay, now the important thing is I'm going to start looking at that difference quotient. So what I'm going to want to create at the end, and maybe I'll write this over, I'm going to create like x naught plus h minus capital F of x naught all over h. So this, the limit as h approaches 0. So this is something I'm going to be going for at the end. So I'm going to start by just looking at, noticing what is f of x naught plus h minus f of x naught. And well, we know that integrals, the limits of integration sum. So if you go from a to b and then b to c, then that gives you the integral from a to c. And then similarly, you can subtract. So if you take one of those sides and subtract them. So we actually know that this integral ends up being the integral from x naught to x naught plus h of f of t dt. Okay, now I'm also going to want to compare this limit with my f of x naught function, because f of x naught is what I want it to be. So I'm going to want to compare these two things. So I want to ask myself, what is f of x naught? Well, it turns out I can also write f of x naught in an integral form because it's a constant. So x naught is just 1 over h times the integral from x naught to x naught plus h of f of x naught dx. Why does it work out to, why is this a reasonable thing to write down? I should probably tell you. Well, notice, what is the integral from x naught to x naught plus h of 1 dx? Well, that's just the length of the interval. It's h. So if I put a 1 over h in front of it, then it's just that over h. So it's 1. And then if I put any constant in here, then it's just h over h times that constant. So all I've done is put a constant in the middle of this integral that integrates to be equal to 1. So that constant doesn't really affect it. But why would I want to do all this? Well, I want to do all this so that I can do a little bit of subtraction and make everything work out really nicely, so that I can take f of x naught plus h minus f of x naught all over h, and I can subtract f of x naught from that. And when I do that, this on the left over here gives me the 1 over h times the integral from x naught to x naught plus h of f of t. And then when I do the other part, I get dt. I get 1 over h. I get the second formula that I just created of x naught to x naught plus h of f of x naught dt. Okay, a few things. So first, that should be a negative sign. That should be a t. Okay, so just a few little typos, but that's okay. So that's subtract. That's not. Okay, so what have I done? I've just replaced my f of x naught with this equation, and then I replaced my my difference equation with that equation. Just replace them with what they are. Okay. Well, this is good. I'm making nice progress now. Well, now that I know these things are continuous, I can put them together. So this difference equation equals, and I'll just put a 1 over h out front, and then we'll have the integral from x naught to x naught plus h of f of t minus f of x naught dt. Well, okay, why was that really useful? Well, that was really useful because this is now less than or equal to 1 over h times, let's slap some absolute values on here. So if I were to slap absolute values on here, and absolute values on here, and absolute values on here, then that's less than 1 over h times the integral from x naught to x naught plus h of the absolute value of f of t minus f of x naught dt, which is less than, well, that came from our continuity. So that's less than 1 over h times the integral from x naught to x naught plus h of epsilon dt. But now notice that this thing right here is just epsilon times that same integral that we set up earlier, which is equal to 1. So this equals epsilon. Okay, well, that's fantastic. So now what we've shown is we've shown what we wanted, and that is that the limit as h approaches 0 of f x naught plus h minus f of x naught all over h equals little f of x naught. Because what did we do? We took this minus this, and we showed that it's less than epsilon. Okay, so there we go. Well, that's part one. So part one says that if you take the derivative of the integral, what do we get out? You just get out the original function itself. All right, let's jump over to part two. And part two is what's generally familiar. Oh, I left myself, look at that, I left myself space to write on and I didn't even use it. Well, sorry, students. I should have been a little bit more, made better use of my space. All right, let's go to part 2 of the fundamental theorem of calculus. And part 2 just says this. It says the integral from a to x of f prime of t dt is equal to f of x minus f of a. And this is exactly what we remember from calculus. And so this just says if you take the antiderivative and then you plug in the endpoints x and a. What do we need to know? We need our little f to be differentiable, and we need f prime to have an integral. So f prime needs to be integrable. Okay, now what we're going to do here is we're going to try to be pretty clever, and I like this proof a lot. So what we're going to do is we're going to go from a to b. We're going to have our function, we're going to split it up into sections. But then what we're going to do is we're going to take each section and draw it, and then we're going to use the mean value theorem to find those points that have the same slopes as the points in between the section, and then we're going to be adding up those original points instead of adding up the derivatives themselves. Sorry, I said that backwards. Yeah, so we're going to use this is the derivative, and so we'll use those points where those things match as our sample points to go backwards from the derivative to the original function. But we're going to use the mean value theorem to find every point within every integral so that we're using that point, and then we're using that point. It's going to all work out just the way that we want it. Okay, great. Okay, so the first thing we're going to do is, as always, we're going to let epsilon be greater than 0. And then because it's integrable, we know that there exists some partition P such that the sum as j goes from 1 to n of f, oh, these are primes, tj delta xj minus the integral from a to b of f prime of t dt. We know that this thing is less than epsilon. So we're going to deal with this partition in which it's very small, and then what we're going to do is we're going to slowly replace this thing with that f of b minus f of a. Okay, but notice that for each interval, for the interval xj minus 1, comma xj, we can use the mean value theorem to find the tj points. Oh, by the way, this inequality should be true for any choice of tj, so any sample points we choose. So we'll use the mean value theorem to find tj within the interval such that f of xj minus f of xj minus 1 equals f prime of tj times xj minus xj minus 1, and this is exactly our delta xj term right here. Okay, well that's great. So what that means we can do, and I tell you what, I will take advantage of my next piece over here. So that means that from the last page, f prime of xj is equal to, f prime of xj times delta xj is equal to f of xj minus f of xj minus 1. So that means that our sum oh, sorry, this was a t here. I wrote the wrong one. F of tj, so because t is our point we chose by the mean value theorem, so that means that sum of f of tj delta xj is the same as the sum of f of xj minus f of xj minus 1. but this is telescoping. And so since this telescopes, all we end up with is the very first term and the very last term. So we end up with f of b minus f of a. So therefore, we get that f of b minus f of a minus that integral from a to b of f of t dt. Well, this is equal to that sum of f prime of tj delta xj minus the integral from a to b of f of t dt. So in short, the mean value theorem lets us replace this sum with the values themselves. So the mean value theorem makes a connection between the values of f and the values of the derivative. But then this is what we started out with, that was less than epsilon. So f of b minus f of a is within epsilon of the integral, and it's just true for all epsilon, so they have to be equal. Okay, I hope you like those two proofs. I find them quite interesting. But at the heart, right, at the heart, we've got that the integral of the derivative equals the original function. But I hope you found these proofs. One thing I like about them is that if you kind of take out the epsilon delta stuff, it's a type of proof you could do with a calculus class, and maybe not all the students would understand it, but your bright calculus students could make their way through the proofs, and I hope that's interesting for you. Okay, there's a number of theorems that fall from this, but I want to focus on the change of variables theorem. So we're going to do the simple version of the change of variables theorem, and that is if phi is continuously differentiable, so phi is C1 and f is continuous. So if phi is C1 and f is continuous, then we get this integral. The integral of, let's write it like this, the integral from a to b of f of phi of x, phi prime of x dx is equal to the integral of phi of a to phi of b of f of t dt. So basically, this is what we know as the change of variables. Some people call the substitution rule. The other one, integration by parts, I'll let you all do that yourselves, and you can work that one out. And I think you may like that. Okay, there's a second version of this where if f isn't continuous, so if I take out continuous, then this left-hand side changes to f of phi of x times the absolute value of phi prime of x dx, and that's a lot harder to prove when it's not continuous and there's a lot more going on. And the vast majority of the problems that we do are continuous, or are what you might call piecewise continuous, and that is we could chop it up into a bunch of pieces and then just do the integral in each piece and add them together. Okay, so let's do this proof and see how it's going to work out. Okay. So the big part of this proof is just looking at each side of the equation and then doing a derivative of it. But to do each side of the equation, we need to kind of think of it as a function. So for this left-hand side, we will think of that as the function g of x, which is going to be the integral from a to x of f of phi of t phi prime of t dt. And that's what's happening over here on the left. And what you'll notice is this is precisely precisely what we had for the fundamental theorem of calculus a second ago. So if I take the derivative of it, I just get f of phi of t times phi prime of t. So that's what the fundamental theorem tells us. Now notice this is where I'm using the fact that f is continuous. So if f is continuous, I can't make this jump, and the whole proof kind of explodes on us a little bit. But let's look at the right-hand side. For the right-hand side, I'll use capital F, and let's not use an x. Let's use, how about y? Just because it might be a different letter than the one over there on the other side. Capital F of y is the integral from phi of a to y of f of t dt, where y is some element in that set phi of a b. So whatever the set is where whatever kind of numbers come out from phi of a and phi of b, y is in there. I'm going to do one quick change before I take the derivative, and that is I'm going to let m be the minimum value of that set. So m is going to be whatever the smallest value is. And then I'll notice that f of y is equal to the integral from m to y of f of t dt plus minus, hold on, minus the integral from m to phi of a of f of t dt. This is just, right, this is just making it where this value here is actually the bottom of whatever that interval is. Let's just not worry about things like negatives and the function going backwards or something like that. We're always going from the smallest value. But then what's nice is what happens if I take this derivative? Well, if I take this derivative, then this last part is just a constant because m and phi of a are both fixed. And so we end up just getting little f of y. Okay, so, sorry. Okay, well, so that's great. So now by the fundamental theorem of calculus, I have these two things worked out. So what I'm going to do is just take my g of x and my f of x and subtract them from each other. And let's just leave these two final results here. And then I'll just say, notice what happens when I take the derivative of this function g of x minus f of x. And the answer is that I get f of phi of t, phi prime of t, minus f of, oh, sorry, those shouldn't be t's. These should all be x's. Oh, phi of x, phi prime of x, f of x. But so that's what I get when I do this. But what you'll notice is this is from the chain rule. This from the chain rule has to equal 0 because the chain rule says those two things have to be the exact same. So what I've done is I've taken my change of variables and put it in a way that it looks like the chain rule. And sorry, I've destroyed this over here. Okay, so that's the real heart of this, is that the chain rule comes. Now, I just have to ask myself, so because that's the case, then that means g of x minus f of x is equal to some constant. But what constant could it possibly be? Well, the constant has to be 0 because if I put like that beginning point, if I put a in, then both integrals themselves are equal to 0. So the constant obviously has to be 0. So that means that g of x and f of x are the same. So the two sides of that equality are equal to each other. All right. Well, I hope that makes a little bit of sense. These proofs are fun. I hope you all are kind of tolerating these difficult proofs. You know, like I said, it's not important that you can recreate all of them, but I think even by learning these, you start seeing the little tricks that go into making proofs run. And so this one, you take the two pieces, you take the derivative of it and show the derivative has to be 0. And then that's how you get the fact that they're actually the same value. So there are lots of ways that these proofs run that can be used or thought of as we move to the future. Okay, there's one last idea, and I'm not going to spend too much time on this because I think you're familiar with it, but we'll do some homework problems related to it. But it's the idea of improper integrals. And that is, up to this point, every integral has been on a closed interval, AB. And what we want to do now is we want to say, well, what if I wanted to do an open interval, A to B? Then what would I do? Well, so what are some examples of some open intervals? Well, 0 to 1 is an open interval, right? Or 0 to infinity is an open interval. So what if I wanted to do an integral with some of these things going on? Well, if you want to do an integral on an open interval, you have to have a couple properties. And the first property is what they call locally integrable. And locally integrable just means that if you're doing some interval AB and you have some C and D inside of there, then that means that f is integrable on that closed set CD. So all we're going to say is that it's local interval means that if we have this open interval, and if I took any closed interval inside of it, then it would fit all the traditional definitions that we've been doing for the last day or two. Okay, so that's a nice result. Now, so that's a nice requirement. And it turns out that we kind of need locally integrable in order to talk about an improper integral. And so all we really do for an improper integral is we think of all of these locally integrable pictures, and then we take the derivative. So what we say is on an open interval, so if f is locally integrable, on AB, but maybe not integrable in the closed set, then we define the integral from a to b of f of x dx to just be the limit of that c to d that we were talking about as the c and the d go out. So the limit of c to d of f of x dx. Now I'm tempted to write something that's actually false here, and I'm tempted to say as c approaches a and d approaches b. And what's false about this is you can't take the two limits at the same time, because if you take them simultaneously, you could get some sort of cancellation going on. So what I should write out, which would probably be more appropriate, would be the limit as c approaches a and the limit as d approaches b of the integral from c to d of f of x dx. And in fact, it only matters because c is approaching a from the right. It really only matters if we take the right and the left-hand limits. Okay, so this is what we define an improper integral to be. And it turns out they have a lot of the same properties as regular integrals, and really all we're doing is once we've defined integrals on these closed sets, then we take the limits of our integrals on our closed sets to get the integral on an open set. So for example, if we're taking the limit to infinity, we might go 0 to n, and then let n go to infinity and look for the limit as that happens. If you want to take the integral of something that maybe has a discontinuity, or maybe is unbounded, I guess discontinuities aren't near as big a deal, but if it's unbounded, then you might take the integral of every small section leading up to that unbounded spot. Okay, I'm going to leave it there. I think I've left you plenty